Hello, my name is Hmida Slimani, graduate student in Material Science, Energy and Nano Engineering Department at Mohammed VI Polytechnic University. I have the pleasure to present to you, dear audience, our work about experimental characterization of electric arc furnace slag under thermal cycling as sensible thermal energy storage material. First of all, I'm going to share with you the outline of my presentation. I will start by the context of study. Then I will pass to thermal cycling and the isothermal test. Then I will present the characterization result and finally a conclusion. Thermal energy storage using sensible material is widely used to match the production and the demand on energy. In this regard, several researchers try to use byproduct materials such as slag as sensible material because it's available and low cost, and check their thermal and mechanical stability for the cited application is mandatory, and our work stands on some uncovered points after thermal cycling of the material. I will start with thermal cycling of the received material, and thus to simulate the charge and discharge operation of thermal energy storage system. We have prepared 3 square samples and we have polished their surface to better visualize the state of surface before and after thermal cycling. The thermal cycling was done in laboratory furnace between 700 degrees C and 270 degrees C using a heating rate of 5 degrees C per minute for 30 cycles. After the 30 cycles, all the samples have been cracked as you can see in the picture. In the second study, we have performed an isothermal study for 2 different porosity samples at 700 degrees C for 140 hours. The results show that one sample have been cracked while the other with the high porosity doesn't crack. We can conclude that the heating rate is too high and causing the pressure increase of gases inside the material which lead to the cracking. Therefore, porosity beside the heating rate has an influence on the thermal stability of the slag material. The visual inspection is not enough, so we have prepared 2 different samples, one as received and the other after thermal cycling for the SM analysis. No further cracking or morphologic modification were detected. The XRD analysis for the received slag show 4 main phases, which are mannite, woostate, gyelinite, and larnate. After thermal cycling or isothermal test, the woostate phase disappeared and the antosity of mannite peak increases, which means that the woostate has oxidized and turned into mannite, which made the material more thermally stable. And that was confirmed by TGI analysis, where we have a slight mass loss in raw material due to the evaporation of volatile compounds, followed by a gain of weight due to the oxidation of woostate phase. After thermal cycling, we didn't detect any significant gain of weight, and that means that we have no oxidation, therefore the material can be considered thermally stable. The XRF analysis show the chemical composition of the slag material in the first table. The major compounds are aluminium, silicon, calcium, and iron in the form of oxides. This composition is in good agreement with the similar slag material reported by the literature from other industries. After thermal cycling of the slag material, we have a slight variation of the chemical composition, and thus due to the oxidation of woostate. We have measured also the specific heat capacity experimentally using DFC technique between room temperature and 400 degrees C, and we found a value of 0.85 kJ per kilogram Kelvin. For the raw material, this value increases a little bit after thermal cycling to reach a value of 0.89 kJ per kilogram Kelvin. And due to the limitation of DFC technique at 400 degrees C, the result was correlated. For high temperature, we have measured the bulk density and skeletal density using Archimedes method and the helium pycnometer method. We found a value of 3.3 grams centimeter cube for the bulk density and 3.9 for the skeletal density. Then the porosity were calculated using the following equation. We found a value of 15%. After the thermal cycling, the skeletal density increases, and that's due to the mannite density is being higher than the woostate one. Regarding the cracking issue, we have shown that the high heating rate leads to the cracking because of pressure increase. In this study, we have used low routine heat of 2 degrees C per minute followed by 3 degrees C per minute to ensure that all the gases escape without increasing the pressure. Therefore, no cracking was detected for the first 5 cycles. Then we have increased back the heating rate to 5 degrees C per minute for the remaining cycle, and also no cracking was detected. Thermal energy storage is a promising technique for the recovery of a huge quantity of waste heat generated by industries during their activity. And the electric arc furnace slag byproduct presents a good thermophysical property. Even the material shows some cracking behavior during the thermal cycling and the isothermal test. The only thing we recommend is slow heating rate during the first few cycles to ensure thermal stability of the material.